what we have to do now is kind of break this down into components, things that we're going to need or to assemble, information we will need, or relationships we're going to need to incorporate into this model to be able to do this successfully. The first one of those, which I'm going to talk about today, is we need a model for the cell characteristics. So before we can do any of this, be able to solve any of these balances, we need a representation of the cell characteristics that's going to tell us how voltage and current density are related as a function of temperature and as a function of the gas composition that we have locally within the cell. We've talked a little bit about the equilibrium voltage. That in itself will go up and down with temperature, and it will go up and down with gas concentration in ways that we've already talked about with the Nernst equation. The rest of this curve that we're seeing, those represent taxes on our reversible potential that we're incurring to drive our different physical processes. So we've got two reactions. We've got an anode reaction. We've got a cathode reaction. Those reactions, we need some driving force to make them go in a forward direction. We also are pushing ions from one side of the cell to the other. At equilibrium, those ions are all equipotential, but to make them move under a steady rate through the electrolyte, depending on the thickness of that electrolyte and its conductivity, we expect some voltage loss associated with that. So, kind of writing this out, V is going to equal equilibrium voltage minus these additional terms that are going to come into play. So what are those terms and why do we end up with this shape, basically, is the thing I want to address. One of the simplest things to think about is the electrolyte. We've got this material which is conducting ions, and that is a macroscopic transport process where we establish a gradient. In this case, it's a gradient in potential, which I'm symbolizing by the Greek letter phi. Phi has units of volts. And as we, over a certain thickness of electrolyte, if we set up a potential gradient where phi is greater in one area and lower than another, that's going to create a driving force for whatever mobile charges you have in the system are to move. In this case, if we're talking about SOFC, it would be an O2 minus ion. If we were talking about a PEM FC, then it would be a proton. That process is ohmic, which means that it's very similar to the linear transport laws that you as chemies are all super familiar with. Newton's law of viscosity, Fourier's law of heat conduction, Fick's law for diffusion. Those are all examples of linear transport relationships where you multiply the gradient times a coefficient to get a flux. The moral equivalent of those three laws that we were used to in transport phenomena is Ohm's law. So we take gradient of the potential, multiply it by the conductivity, and that gives us the current density in amps per square centimeter. One really major difference between conduction processes, which we're describing here, and diffusion processes, which you're familiar with, is that current is contiguous. There's no accumulation of charge. If you think about diffusion, you can have variations in concentration and accumulation in space. If you take a drop of dye and you stick it into a big medium, the color will spread out over time. And you can calculate del dot of the flux is equal to the dc dt, or the local accumulation of whatever it is that's diffusing. Unless you're talking about very high electric fields, charges can't accumulate in space. The forces are just way too big. Current has to flow from one place to another. It can't flow in and not flow out. That means that del dot of the current density in the electrolyte is zero everywhere. So those two together, we take Ohm's law, which is basically like Fick's law, but for conduction, and then we couple that with charge conservation, which is forcing the divergence of the current density to be zero. Put those two together, and we can solve them in whatever geometry to figure out what the current density distribution will look like. If it's one-dimensional, and we just have one axis of variation, so potential drops from one side of the cell to the other along one-dimensional axis, then current density would equal sigma I, which is the conductivity, times the difference in potential divided by the length, or the distance that it's traveling. Flip that around, it's saying that the voltage loss associated with current flow through the electrolyte of thickness L is given by L over sigma. So we get this simple resistance, it's an area-specific resistance equal to L over sigma. So the main takeaway is that the polarization loss that you have for an electrolyte varies linearly with the current density. It's also proportional to the thickness. So if I make the electrolyte twice as thick, I'm going to have twice as large an ohmic resistance. So what does that look like on our polarization curve? It would just be a straight line. As we increase the current density, the voltage loss would linearly increase. So at a minimum, even if the electrodes were completely reversible, we would have a voltage that would linearly drop from the open circuit voltage as we increase the current density just due to the electrolyte resistance. The next thing that's important is the electrodes themselves. The physics of conduction of ions through a medium is really well-established theory. Electrodes, on the other hand, are very complicated systems. We tend to measure their characteristics. We don't necessarily always understand those characteristics very well, but we can describe them. And a common way to describe them is in terms of something called an overpotential. An overpotential basically represents a voltage loss that you're incurring to drive the current at whatever level. And unlike ohmic resistance, it tends to be very nonlinear. The lower in temperature you go, the more nonlinear it tends to become. Roughly speaking, it looks like what I've just drawn up on the screen. So as you increase the current density, the voltage loss goes up, and it tends to go up more dramatically at first at low current densities. This is called the activation loss. It basically sort of means I've got to kick up the driving force up to a certain threshold in order to kind of get the current to go. And then once I've reached that threshold, further increases in current density don't cost as much. In a polymer electrolyte fuel cell, it's very dramatic. Like if you actually isolate the overpotential for a particular electrode and measure it, it tends to go suddenly upward and then become very flat as you continue to increase the current density. SOFCs, it's a bit more gradual. I will talk about one simple model for why it looks this way. It's an empirical model, but it kind of gets at the basic issue. It's called Butler-Volmer kinetics. It is theoretically a true statement, actually, for certain types of single electron transfer reactions at interfaces. So it has some semi-theoretical basis. The basic idea is you can think about current flows or electrochemical rates as a competition between two processes, a forward rate and a backward rate. If I have an oxidation reduction process going on, like hydrogen oxidation at the fuel at a SOFC anode, under polarization, H2 plus O2 minus is going to go to water. But when the current density is 0, that process actually still happens. It's just that the equal and opposite process of H2O splitting apart into H2 and O2 minus is happening at the same time at an equal rate. So it's sort of like you have the forward rate. Forward rate is like that big. If I think about a vector, right? Here's one vector. Forward rate is this big, right? And the backward rate is equal and opposite. So with those two things happening all the time, the net rate is 0. The net current density that you measure is 0 in a state of equilibrium. So then what we do is we start to perturb that equilibrium by making the forward rate a little bit faster, and we suppress the backward rate. We make the backward rate a little bit slower. And so as long as the forward rate is a little bit bigger than the backward rate, then we get a net rate in the forward direction. That's what this equation basically captures. So the two terms, an e to the alpha f eta over RT, that's the forward, that represents the forward rate. And then we have an exponential term, which represents the backward rate. And you'll notice the structure, there are two exponentials. If I take the overpotential, which is eta, this Greek symbol eta, if I make the overpotential 0, then I get e to the 0, which is 1, minus e to the 0, which is minus 1. So 1 minus 1 is 0. And so the current density automatically goes to 0 when the overpotential goes to 0, just mathematically. The other term that's in here is this exchange current density. It's called the exchange current density. It has all the units in it. So it has the units of amps per square centimeter, just like current does. And what it represents is how fast is the forward rate and the backward rate in terms of amps per square centimeter when you're in equilibrium. To first approximation, what many people will do is assume that I0 is not a function of eta. So as long as you're not making eta go crazy to some ridiculously high level, then we think about I0 as being a constant. So then the other parameters in here have to do with how easy it is to activate these reactions. Alpha F, this is a number of order unity, and it's considered a constant. So it's usually of order 1, it might be a half, that kind of order of magnitude. And what it basically represents is how much the transition state energy shifts around when you create a driving force for the reaction to take place. This is affected by temperature because it's an activated process, meaning we have some probability of an event happening and going over a barrier, just like in chemical kinetics. And we make the temperature higher, then the rates tend to get higher because we can get over that barrier more easily due to thermal fluctuations. Normally, these are called the anodic and cathodic transfer coefficients. The reason I like to describe it with a forward and backward instead of an anodic and cathodic is because this same equation is often used for both the anode and the cathode. For the anode, there would be an exchange current density for the anode, and then there would be an anodic transfer coefficient for the forward rate and a cathodic transfer coefficient for the backward rate. And we have an overpotential for the anode, so that's eta anode. So that's what this Butler-Volmer equation reduces for the anode. And then at the cathode, if we apply the same equation, we would have a cathode exchange current density, a cathode overpotential, and the forward rate coefficient alpha F would be described as the cathodic transfer coefficient, whereas the backward would be described as the anodic transfer coefficient. So it doesn't mean it's the anode, it means it's the anodic direction of the cathode. And this, likewise, over here, alpha C, this is the cathodic direction for the anode. There, in the electrochemistry world, there are two important limits of this equation that you'll often hear people describe. One is the linear limit. If you take the Butler-Volmer equation and you look mathematically where the current density gets small, as eta gets small, then this becomes an exponential close to 1, which we can do a power expansion on. So this would become 1 plus alpha F eta over RT, and this would become 1 minus alpha F eta over RT. And the ones cancel, and so the first order term in alpha, those two would combine, two negative signs canceling. So this would end up being I0 times alpha F plus alpha B times F eta over RT. So what that tells us is that for small currents, current is roughly linear in eta. And that's what we see in this curve. If you look at small eta, there's a finite slope here, and that slope goes to a constant as we get to very tiny current density. And it basically has a resistance value, which is a lumped parameter. It includes alpha F plus alpha B multiplied by I0. That all is contributing to this resistance that you observe. And then the other limit is called the Tafel limit. If you drive eta very big, then this exponential blows up and becomes enormous. Whereas this one, because I've got a negative sign here, this backward rate term just shrinks to nothing. And the entire behavior becomes dominant completely by the forward rate. And so to first approximation, I scales as e to the alpha F eta over RT. This is called the Tafel limit. And in that limit, if I take the logarithm of both sides, what we see is that the log of the current density will scale with linearly with the overpotential. So if you plot log of current versus eta, you should start to see a straight line. And that's called the Tafel limit. So sometimes people will just measure this part and focus on that, and then they'll just extrapolate into the linear region as an approximation. Okay, so last thing I will mention is mass transfer losses. Another thing that can happen in a fuel cell is that under polarization, you may be drawing current so quickly, you may cause the gas concentration near the electrode surface to become depressed, because like if you're using up hydrogen, you would have a lower hydrogen concentration near the cell. Likewise, in the drawing I have here, I'm picturing a cathode where the oxygen concentration at the cathode of the SOFC has become very small because we're driving the current so fast. And if this oxygen has to diffuse through a medium to get to the surface, then there's a concentration difference. I'll have a low concentration of oxygen near the cathode, a high concentration out here in the air compartment, and that actually contributes to the voltage loss because of the Nernst potential. And to see that, what I have here is just written is, here's the Nernst potential I've written this for a methane oxidation reaction. What's going on at the anode doesn't matter, just focus on the oxygen dependence. So I've got a certain oxygen concentration dependence in the Nernst potential. If I make the concentration near the surface get smaller, that impacts the reversible potential. And I can isolate that by just rearranging this, um, separating the surface part, which is differing from the bulk, and write it as the reversible potential, assuming you had equilibrium with the gas and the bulk, minus a term, which is the log of the pressure ratio between the channel where the oxygen is at full concentration versus the surface where it's at low concentration. So basically you get this shift in Nernst potential just due to the difference in concentration. And what we can do now is stick in laws of diffusion. So if I have, for example, Fick's law, let's say imagine we solve Fick's law of diffusion, oxygen has to diffuse over a length L. We could solve the concentration profile. That gives us a certain flux of oxygen through this medium that's proportional to the diffusion coefficient divided by the thickness times delta P over RT. Well, I can take all that, substitute it back into our voltage displacement for whatever current density. We can figure out what the concentration displacement has to be. What we end up with is a displacement in voltage, which looks like this. So it has almost no effect at small current density. But then as we get higher and higher in current density, eventually we keep suppressing the concentration of oxygen in this case. If we go to zero, then the Nernst potential blows up, and all of a sudden we get a massive voltage loss that's associated with this Nernstian displacement of the concentration as we approach this critical current where we deplete all the oxygen. That's called the limiting current. So putting that all together, we end up with a curve that looks like this. I have the open circuit voltage that depends on concentration and temperature within certain ways that we already know about. But we're now adding three different things. We've got an electrolyte resistance, actually four different things. Electrolyte resistance, which is linear. We have a cathode overpotential, which varies nonlinearly with current, usually an anode overpotential that varies nonlinearly with current. And then we can also have this additional voltage displacement associated with a transport limitation. You add those together, or rather subtract them all from the open circuit potential, and that's what you end up with as the polarization curve. So what's good about thinking about this way is that if we know something about all of these processes, we know the thickness of the electrolyte, we know its conduction, we know some measurements of the anode and cathodic characteristics, we can actually take that stuff, plug it into a model, and fit it to data. So we can take data that someone's measured from a cell, could be in the literature or something we measure ourselves, and we can make a function that allows you to interpolate and extrapolate from conditions that you've measured or others have measured to make predictions about what the cell will do in a stack.